Okay, so welcome back to this next video in which we are discussing voltage-gated ion channels. Okay, right, so we're currently in the process of discussing voltage-gated potassium channels. Okay, and we've just been discussing permeation and selectivity of the open voltage-gated potassium channel. What I now want to turn my attention onto is the topic of inactivation of voltage-gated potassium channels. Okay, right, so we saw this when we were discussing the action potential, okay? Basically, even if you depolarize the electrical potential difference across the cell membrane, it will cause the voltage-gated potassium channel to open, but it doesn't stay open for very long. It closes very quickly if you keep the electrical potential difference across the cell membrane depolarized. Okay, so what we know is that if we start off at negative 65 millivolts, we know that the channel will be closed because the V-gate is closed, because the S6 helices are impeding on the central pore, basically, and stopping potassium ions from being able to move through the pore of the voltage-gated potassium channel. We then know that if we depolarize the electrical potential difference across the cell membrane up to above negative 40 millivolts, that results in the S4 helices moving upwards, and then that pulls on the S4-S5 linker, which results in the outward movement of the S6 helices. Okay, however, let's say we maintain the electrical potential difference depolarized for a long period of time. The voltage-gated potassium channel does not remain open for that long period of time, basically, because a different mechanism now closes the channel, a mechanism other than the S6 helices blocking the pore, basically. Okay, so the S6 helices, they remain outwards, okay, as long as you've got the electrical potential difference across the cell membrane depolarized of the threshold potential, then the S6 helices will not be blocking the pore, basically. So a different mechanism is now going to block the pore, okay, and these are the inactivation mechanisms. Now, there are two different types then of inactivation. There is fast type inactivation, okay, called fast inactivation, and fast inactivation also has another name, okay, and we'll see the basis for this other name later on. Fast inactivation is also called N-type inactivation. Okay, and this is the main type of inactivation. This is the one which occurs within a few milliseconds of the voltage-gated potassium channel actually going into the open state. So normally this is the one that actually shuts the channel first, even though the electrical potential difference across the cell membrane is still depolarized of the threshold potential. Okay, some voltage-gated potassium channels, however, do not have fast inactivation for reasons that we will discuss, and they still inactivate, however, but with a totally different mechanism that is much less well understood, and we're going to be able to say much less about it, which is called slow inactivation, okay, which is also called C-type inactivation. Okay, so there is N-type inactivation and C-type inactivation, or slow-type inactivation. Okay, and more is known about fast-type inactivation. Okay, right. Now, basically what I should stress is the fact that after the channel has inactivated, after it's closed, even though the electrical potential difference is still beyond negative 40 millivolts, okay, and the channel has closed through this other mechanism, this inactivation gate closing, rather than the V-gate closing. The V-gate is still open. Okay, if you now want to reopen this inactivation gate, if you want to reverse the inactivation, you have to take the electrical potential difference back down to repolarized levels, back down to negative 65 millivolts. So if you repolarize the cell membrane, that undoes this inactivation gate, both of these types of inactivation. It will undo whatever it is that is blocking the pore through fast and slow inactivation. But then, of course, the problem is that once you've repolarized that like that, the V-gate will then close anyway. So the fact that you have reversed the inactivation gate being closed doesn't really matter, because you've now reversed the inactivation gate being open, so the channel is still going to remain closed. Okay. But it's important to note that these two gates, they will be reopened basically by repolarization of the electrical potential difference across the cell membrane. And I will come back to that point and put it down more formally on paper once we've actually discussed the mechanisms underlying fast type inactivation and slow type inactivation. Okay, right, so let's begin with fast type inactivation then. Okay, this is a nice, easy, conceptual one to understand. The C-type inactivation one, that's more controversial. Okay, right, so fast type inactivation results by this ball or chain mechanism. It results because basically a structure on the intracellular aspect of the voltage-gated potassium channel is capable of going into the open internal aspect of the pore and blocking it, basically. So let me discuss this structure. Okay, so I'm going to redraw out the structure of an individual alpha subunit of a voltage-gated potassium channel, and I'm going to now dwell on something that I didn't dwell on before and didn't even show before. Okay, so this is the structure that we have seen before. Here are the membrane spanning portions. Here is the C-terminus, and we've seen that there is this T1 tetramerization domain there, so that's T1. But now I'm going to add in a new structure prior to T1 here that is present on many alpha subunits of voltage-gated potassium channels, but the reason that I did not show this previously is because it's not present on all of them. Okay, the structures that I was highlighting previously when we studied this were the structures that are present for absolutely all of those 40 different types of voltage-gated potassium channel alpha subunits. Okay, whereas this structure that I've now just added on is not present for all of them, but it's present on most of them. Okay, so and this structure here then, this is called an inactivation ball, and this is what's going to underlie the fast type inactivation. Now the alpha subunits of voltage-gated potassium channels that do not have an inactivation ball, they have special names. They are called the non-inactivating subunits. Okay, however, we will see how these non-inactivating subunits of voltage-gated potassium channels can still actually produce you voltage-gated potassium channels which can have fast-type inactivation. Okay, that's going to involve the beta subunits, the accessory subunits that we haven't yet discussed. So we will come back to that point. Hold that thought in your head that these non-inactivating subunits that don't have inactivation balls can still actually assemble into voltage-gated potassium channels that can show fast type inactivation, because you can add on accessory subunits, these beta subunits, which then do have separate inactivation balls on them. So we'll come back to that point. Okay, however, many voltage-gated potassium channel alpha subunits do have this structure prior to T1 called the inactivation ball. Okay, and the inactivation ball is a cluster of around 20 amino acids, so it's a little portion of the polypeptide of around 20 amino acids in length, and it really does form a sort of ball structure, basically. Okay, so what I now want to do is draw you a picture of a voltage-gated potassium channel tetramer that is going to be made out of alpha subunits that all do have inactivation balls. So they are alpha subunits that are not non-inactivating subunits. Okay, so I'm going to redraw out that picture that we had of a voltage-gated potassium channel tetramer. Okay, so a lot of initially this picture will be a repeat of what I've shown earlier. Okay, but I'm just going to add on the inactivation balls, but it doesn't hurt to repeat what we've done earlier, okay, because it's quite a complicated picture. Okay, right, so here is the pore forming domain, okay, once again made out of these 4 alpha subunits pore forming domains here. Okay, so I'll divide it up into the 4 separate pore forming domains from the 4 separate alpha subunits, and now let me just put in the voltage sensing domain. So here is the first voltage sensing domain, then we'll have another one here like so. Okay, another voltage sensing domain at the back there. Okay, like so. And then the 4th voltage sensing domain over here. Okay, right, and then I'll just colour this in, and I'll once again colour code it on a subunit basis. So I'll colour each alpha subunit in a different colour. So we'll have this one once again shown in red here. Okay, so this is one subunit of the voltage-gated potassium channel, and then again over here is its voltage sensing domain here. Okay, and remember the voltage sensing domains and the pore forming domains, I keep stressing this point, but it's so important to understand, are not sitting next to each other, they're separated in this way. Okay, we'll colour the next subunit of the voltage-gated potassium channel in blue. Here is its voltage sensing domain, and here over here, this is the pore forming domain of that blue alpha subunit of the voltage-gated potassium channel. Next up, we'll have the next one in green here. Okay, so here is its voltage sensing domain, and here then is the pore forming domain of that green subunit there. And then finally, the fourth subunit will be in orange here. Here is its voltage sensing domain. Okay, and then in the centre here is its pore forming domain. Okay, next what I want to show is the T1 tetramerization domains all tetramerized together, and now I want to add on the inactivation balls. Okay, and then I'll show you the path that the inactivation balls take to inactivate the voltage-gated potassium channel. Okay, so firstly let's just put the T1 tetramerization domains on here. Okay, and remember each alpha subunit's T1 tetramerization domain will be under the voltage sensing domain rather than the pore forming domain of that individual alpha subunit. Okay, so for instance, the red subunit's T1 tetramerization domain will be up below the voltage sensing domain of the red subunit here. Okay, the blue subunit's T1 tetramerization domain will be below, when we didn't put that line there, so I'll just put that in there, will be below the voltage sensing domain of the blue subunit here. Okay, the green subunit's T1 tetramerization domain will be below its voltage sensing domain here. And then finally we'll have the orange subunit's T1 tetramerization domain over there. Okay, and now I'll just add on those connections between the T1 tetramerization domains and the voltage sensing domain, okay? So there's the connection for the red subunit. Here's the connection for the blue subunit. Here's the connection for the green subunit there. And finally the connection for the orange subunit, and that should be going to the orange subunit's voltage sensing domain, not its pore forming domain. Okay, and we've discussed before that what that creates is these natural windows through which potassium ions which want to gain access to the internal aspect of the pore must go through. So they're going to have to go through these natural windows, one of these four natural windows, either between this dangling down bit here from the red subunit and this dangling down bit for the blue subunit, or between one of the other three combinations that you could have. Okay, so through one of those four natural windows basically. Okay, so now what I want to do is add on the inactivation balls. So let's say that this voltage-gated potassium channel tetramer here was made out of four subunits that all have inactivation balls. So the red subunit, the blue subunit, the green subunit, and the orange subunit are all going to have inactivation balls. So let me now put them on here. Okay, so we will start with the red subunit's inactivation ball, and I think I'll make the little connection a bit bigger. Okay, so here is the connection. Okay, then we'll have this inactivation ball here. Okay, and then finally you'll end up with the N terminus here. Okay, in addition we'll have it for the blue subunit here. Here is its inactivation ball, like so, and here is its N terminus. Continuing on, we'll do it for the green subunit here. Okay, here is its inactivation ball. Okay, after the T1 tetramerization domain, or of course you could view it as before the T1 tetramerization domain. After all, this is the start of the protein here. Okay, and then finally I'll put in the orange subunit's inactivation ball here. Okay, so there it is, and here is the orange subunit's amino terminus. Right, okay, so there is our voltage-gated potassium channel tetramer constructed out of these 4 alpha subunits which all have inactivation boards. Okay, so this is the principle then of fast type inactivation, and fast type inactivation is going to occur within 1 to 2 milliseconds of the channel being open. Okay, firstly let me actually just tell you the reason it's called N-type inactivation. Okay, the reason it's called N-type inactivation hopefully should be pretty obvious. It's because it's going to involve these inactivation boards which are at the N terminals of the alpha subunits of the voltage-gated potassium channels. Okay, right, so let me go through what's going to happen here. So we start off with our voltage-gated potassium channel sitting in the cell membrane, and I'll just be brave and put some cell membrane there. Okay, so there's the cell membrane. It's sitting in the cell membrane. Initially, the electrical potential difference across the cell membrane was, let's say, negative 65 millivolts. And at that electrical potential difference across the cell membrane, the channel will be in the closed resting state, okay, where the S6 helices are impeding in on the internal pore and stopping potassium ions from moving through. When we depolarize the electrical potential difference up to negative 40 millivolts, all of the voltage sensing domains will bounce up a little bit, okay, because the S4 helices are bouncing up. That will then communicate to the pore-forming domains of each of these alpha subunits via the S4, S5 linkers, which remember are these links between the voltage sensing domain here and the pore-forming domain, there shown for the red subunit. Okay, and that will lead to the S6 helices moving outwards, basically, and therefore we have opened the V-gate. Okay, so the V-gate is no longer blocking the pore, and for 1 to 2 milliseconds, you will actually have an open pore, and potassium ions will be able to move through that pore, and you will get a huge number of potassium ions passing through that pore in those 1 to 2 milliseconds. Okay, then what's going to happen is one of these inactivation balls, okay, from one of the alpha subunits is going to end up blocking the pore, and it's just a stochastic process as to which one it ends up being. It's just chance, basically. Okay, so any one of these 4 inactivation balls could do it. Okay, but what happens, let's say it will be the blue one here, is it will go through the lateral window just like a potassium ion would. Okay, so it will go through like so, through this lateral window, into the internal aspect of the pore, and then it will block the pore, basically. Okay, and this sort of a mechanism is called a ball and chain mechanism. Okay, because basically the inactivation ball is a ball and it's on a chain, and then it's inserting into the pore to block it. So this kind of an inactivation mechanism is called a ball and chain mechanism. However, it turns out that the opening to the internal aspect of the pore is not actually wide enough for the ball to fit in. So we think that actually the analogy to a ball and a chain is slightly incorrect, basically. Okay, it turns out basically that the internal opening of the pore is actually only around 6 angstroms. Okay, and if you don't know what an angstrom is, 1 angstrom is just 1/10 of a nanometer. Okay, so 1 angstrom is 0.1 nanometers. So it's just another unit for length that people use on this tiny scale, basically. It's a very biologically relevant length scale to be using. Okay, so the diameter of the internal aspect of the pore is around 6 angstroms, whereas this ball here of 20 amino acids, this inactivation ball, is far too thick to actually fit into the internal aspect of the pore. Okay, so we think that what actually ends up happening is the inactivation ball ends up unfolding out of being a ball, okay, and it unfolds into a sort of linear peptide, like so. So here, this is meant to represent the inactivation ball that is now unfolded, basically. And it's now just a linear polypeptide. And we think that that then slithers like a snake into the internal aspect of the pore, basically. Okay, so we think that really it's more like this. Okay, so if I show this, here is the internal aspect of the pore, we think that the inactivation ball slithers like a snake into there, and you've got to imagine that this is a little bit out of scale. It would be much tighter fit, basically, in reality. Okay, so we think the inactivation ball unfolds into a linear polypeptide, and then that slithers up the internal aspect of the pore and ends up completely blocking the pore. Okay, and that's what occurs in fast type inactivation. Okay, right, so that occurs within a few milliseconds, basically, and in order to reverse this sort of blockade, you have to repolarize the electrical potential difference across the cell membrane. So if you take the electrical potential difference across the cell membrane back to negative 65 millivolts, that ends up pulling the inactivation ball out of the internal aspect of the pore. So the inactivation ball will come back out once you repolarize the electrical potential difference across the cell membrane. Until you do that, it won't work, basically. Okay, until you do that, the inactivation ball in this unfolded form maybe will stay lodged in the internal aspect of the pore. Okay, so you have to repolarize the electrical potential difference across the cell membrane to pull the inactivation ball out. Okay, so something about the electrical potential difference across the cell membrane is controlling the activity of the inactivation balls, basically. But then, of course, once you've repolarized the electrical potential difference across the cell membrane, yes, you can remove the inactivation ball now, but of course the S6 helices, as soon as you remove the inactivation ball, will then just return to impeding the internal aspect of the pore anyway, so it will go back to the original state. Okay, so that's fast type inactivation. Now let me mention this other type of inactivation, so C-type inactivation, which is called C-type inactivation because it occurs much more towards the C-terminal portion of the alpha subunits of voltage-gated potassium channels rather than the amino terminus like the inactivation balls occurs. Okay? Right, so basically, how do we know C-type inactivation occurs? Because it occurs much slower than N-type inactivation. Okay, and N-type inactivation is the main really important one that inactivates the channel first, and then surely it wouldn't be that of a C-type inactivation is actually occurring because once it's closed, it's closed. Okay, however, basically, even if you take a voltage-gated potassium channel, which is built out of alpha subunits that don't have inactivation balls, so take a voltage-gated potassium channel where all of the alpha subunits don't have inactivation balls, and they don't get around this problem with beta subunits. We'll talk about how you can get around that problem with beta subunits in a moment. Okay, no inactivation balls whatsoever in the voltage-gated potassium channel. Okay, the voltage-gated potassium channel can still actually inactivate, basically. So what I mean by that is that if you depolarize the electrical potential difference across the cell membrane, it will open transiently, but then if you maintain the electrical potential difference across the cell membrane in this depolarized state, it will not remain open for that long. It will go into another type of closed state that is different from the closed state where the V-gate is closed. Okay, so what closes in these channels that don't have inactivation balls to block their pore? Okay, well, it's believed to be a change on the level of the selectivity filter. Okay, so something changes about the selectivity filter that then stops potassium ions actually being able to move through the selectivity filter. Okay, so what is this change? Well, for a very long time it was believed that the change that occurred was that the selectivity filter constricted, basically. Okay, so we believed that the selectivity filter was going to get narrower, and then that was what was going to stop potassium ions from being able to move through. Okay, however, there is starting to be voiced the opinion that maybe in fact what happens is the selectivity filter dilates. Okay, so it could be the exact opposite. It could either be constriction or dilation. Okay, just something that means that potassium ions can't interact with those four sites as well, basically, and therefore potassium will stop moving through. So it could either be constriction, which would mean that the potassium ions were now too big to actually fit through, or it could be dilation, which means that they're now too small to go through in a thermodynamically favourable way. Okay, we don't know. It's still an area that's being actively researched. Okay, we know very little about C-type inactivation, but what we do know is that even in these voltage-gated potassium channels, which don't have N-type inactivation, they don't have any of these inactivation balls to plug up the internal aspect of the pore, you still get inactivation. It's a slower type of inactivation. It takes longer than N-type inactivation to occur, but something changes on the level of the selectivity filter to stop potassium ions actually moving through it. Okay, what I want to now talk about is I want to summarize all of what we've talked about with regards to inactivation into a little flow diagram and give you some key bits of terminology, okay, and talk a lot about the fact that the inactivation can be reversed by repolarization, because that's a really important concept. Okay, right, so I'll just get another piece of paper to do this. Right, okay, so I'm going to draw a basic flow diagram for this. So, the voltage-gated potassium channel then, it starts off in this closed state, okay, where the V-gate is closed, okay, so the closed state of the closed state of a voltage-gated potassium channel means the state where the V-gate is closed, okay, so where the S6 alpha helices are impeding on the internal aspect of the pore and stopping potassium ions from moving. Okay, we know that the closed state can be induced to go into the open state, where the S6 helices are no longer impeding the internal aspect of the pore, okay, and you also don't have anything else impeding the aspect of the pore, and this is done by depolarization. Okay, and this process, a key piece of terminology here, this process of taking it from the closed state to the open state, that is called activation. Okay, so you can activate the channel by taking it from the closed state to the open state, opening the V-gate by depolarization of the electrical potential difference across the cell membrane. Okay, now, let's say you return the electrical potential difference across the cell membrane back down to the negative 65 millivolts extremely quickly before any inactivation mechanisms have occurred. Then you can return it back from the open state to the closed state just by closing the S6 alpha helices once again, so getting them to re-impede the internal aspect of the pore. That process of taking the channel from the open state to the closed state is not called inactivation, it's called deactivation. Okay, so repolarizing the electrical potential difference across the cell membrane will cause the V-gate then to reclose, and that process of taking the channel from the open state to the closed state once more is called deactivation. Okay, so depolarization causes activation, repolarization causes deactivation. Okay, we've then talked about the fact that if you keep the electrical potential difference across the cell membrane depolarized at the threshold potential for a long period of time, then what will happen is the channel will not just remain in the open state, basically. It will go into a third state called the inactivated state, and we've talked about how there are two actual different mechanisms of inactivation. There's this mechanism where this ball, this inactivation ball, will block the internal aspect of the pore, okay, in those voltage-gated potassium channels which have inactivation balls, okay, and there's also this mechanism which causes some change in the selectivity filter that stops potassium ions actually being able to move through the selectivity filter. Now, in certain types of voltage-gated potassium channels where you have inactivation balls, you will have both of those going on at the same time. So you'll have the internal aspect of the pore blocked by an inactivation ball, and at the same time you'll have this change occurring to the selectivity filter to stop potassium ions moving through. Okay, and the potassium channel will now move into this inactivated state then. Okay, so I'll colour in the inactivated state in red. Okay, so if you remain depolarized, then the open state channel will go into the inactivated state, and that process is called inactivation. So do not confuse inactivation and deactivation. Deactivation refers to the open state going back to the truly closed state, where the V gate is closed. Okay, inactivation refers to these different gates closing. Okay, so the N gate, which is this inactivation ball, plugging in the internal aspect of the pore, or the C-type gate, which is this collapse of the selectivity filter, either by constriction or by dilation. Okay, right, and that is induced by the depolarized electrical potential difference. Those two gates, okay, the N-type gate consisting of this inactivation ball, plugging the internal aspect of the pore, that is caused by the depolarized electrical potential difference, okay, because we know that if we reverse the depolarization of the electrical potential difference, the N-type gate will reopen, okay, the inactivation ball will get out of the internal aspect of the pore, okay, so that N-type gate is again a voltage gate. It's determined by the electrical potential difference across the cell membrane, but it's the opposite type of gate to the gate that we had here. The V gate was being opened by depolarization. The inactivation gates, both the N-type gate and the C-type gate, they are closed by depolarization, okay. And we've talked about the N-type gate. Now let me just mention the C-type gate. The C-type gate is also closed by depolarization, okay? It just takes longer to occur than the V gate takes to open, and also than the N-type gate takes to close, okay? So C-type gating, this collapse of the selectivity filter, this is triggered by depolarization of the electrical potential difference across the cell membrane, okay, and it will again be reversed when you repolarize the electrical potential difference across the cell membrane, okay. So both of these processes, both activation, the opening of the V gate, and inactivation, the closing of the N gate and the C gate, these are both triggered by depolarization, basically. All that really is important here is that the V gate is much quicker to respond than the inactivation gates. So the V gate has opened before the inactivation gates have closed. Okay, and that's why you temporarily get this open state before the inactivation gates then close. Okay, and then stop conduction. Okay, right, so depolarization causes both of those. And then when you repolarize the electrical potential difference across the cell membrane, that will then cause the inactivation gates now to open again. Okay, so they will reverse, and that process of the inactivation gates opening when you repolarize the electrical potential difference, that is called de-inactivation. Okay, so another piece of terminology here. De-inactivation refers to the inactivation gates going from being in the closed state, so where the N gate is plugging in the internal aspect of the pore and the C gate is collapsed so that no potassium ions can move through it. Okay, the process of those reopening, basically, which occurs when you repolarize the electrical potential difference across the cell membrane, that's called de-inactivation. And then after de-inactivation has occurred, you'll temporarily go back into the open state for a transient, flash, and then of course the V gate will reclose because you've repolarized the electrical potential difference, so you'll undergo deactivation. Okay, so de-inactivation and deactivation then, they are driven by repolarization. Okay, so those are some important pieces of terminology with regards to inactivation and the mechanisms underlying it. Okay, right. So that is why voltage-gated potassium channels do not remain open for a very long time when you actually depolarize the electrical potential difference, because the V gate is not the only one responding to the depolarization in the electrical potential difference. You've also got these two types of inactivation gate in many types of voltage-gated potassium channels. In some you'll only have one type, which is the C-type inactivation gate, but regardless, in all voltage-gated potassium channels you will have some sort of inactivation gate, which is also triggered by the depolarization in the electrical potential difference across the cell membrane, and that will then try and close the pore, basically, and stop potassium from moving through the pore of the voltage-gated potassium channel. Okay, and then when you repolarize the electrical potential difference across the cell membrane, you will then reverse all of the gates. So you will open the inactivation gates, a process called deinactivation, and you will close the activation gate, a process called deactivation. And therefore you'll go back to the closed resting state and you'll be ready to do it all again. Right, so the next and final thing that I want to talk about voltage-gated potassium channels is the beta subunits of voltage-gated potassium channels. Okay, because these can be an addition that you can add on to voltage-gated potassium channels, which can then allow voltage-gated potassium channels which have no inactivation bores on their own to then have inactivation bores. So it can change the inactivation properties of voltage-gated potassium channels. Okay, so we've talked a lot then about the alpha subunits of the voltage-gated potassium channels, which are the essential ones. You don't need beta subunits to build a voltage-gated potassium channel. The beta subunits are also called the accessory subunits. Okay, they're things that you can add on which will change some of the properties of the voltage-gated potassium channels. Principally, the one that we're going to talk about is inactivation. They can change the inactivation of voltage-gated potassium channels. They can give voltage-gated potassium channels which don't have N-type inactivation gates, N-type inactivation gates. Okay, right. So let me firstly tell you about how many different types of beta subunit there are, and then I'll tell you about where they actually attach on, basically. Okay, right. So there are 3 different beta subunits of voltage-gated potassium channels, so much more easy than the 40 different alpha subunits. Okay, and these are called KV beta. Okay, so voltage-gated potassium channel beta subunit, and then there's KV beta 1, KV beta 2, and then finally KV beta 3. So this is the naming system for the 3 beta subunits of voltage-gated potassium channels. Okay, right. So these proteins are globular proteins that can attach onto the intracellular aspect of an alpha subunit of a voltage-gated potassium channel. Okay, so if I just get back my picture of the voltage-gated potassium channel tetramer. Okay, so this picture here. So let's now imagine that we have got a tetramer of alpha subunits of voltage-gated potassium channels, all of which do not have inactivation bores. So we have got a tetramer of non-inactivating voltage-gated potassium channel subunits. Okay, so these inactivation bores, vanish them away basically, they're not there. Okay, what we can now do is attach onto these non-inactivating alpha subunits, beta subunits, and they can provide the inactivation bores that will then give the voltage-gated potassium channel the ability to have an N-type inactivation process. Okay, and I should stress that these beta subunits, you don't just attach them onto non-inactivating subunits, you can attach them onto subunits that have inactivation bores of their own, and then the beta subunit can just alter the speed at which inactivation bores will actually plug up the internal aspect of the pore of the voltage-gated potassium channel. Okay, so beta subunits are not just something that you can attach on to non-inactivating alpha subunits, they are something that you can attach on to all sorts of different alpha subunits of voltage-gated potassium channels. Now, where are they actually going to get attached? Well, they get attached to this N-terminal region here. Okay, so what you're going to end up with is another tetramer of 4 beta subunits dangling below here. Now I don't want to have to draw out this entire picture again, so what I'm going to just do is take the portion from below here, take the T1 tetramerization domains, redraw those out, and then I'll draw the beta subunits dangling below, basically attached to the alpha subunits on the cytoplasmic aspect. Okay, right, so that's what I'm about to draw then. So here are the T1 tetramerization domains of our 4 alpha subunits of the voltage-gated potassium channel, which are all tetramerized together like so. Okay, so I'll colour these all in separate colours once again. Again, I'll try and get the colour coding the same. So bringing back up this picture, we want red, blue, green, and then orange. So let's just put that on. So here is the red subunit's T1 tetramerization domain here, which will be below the voltage sensing domain for that red subunit. Okay, here is the blue subunit's T1 tetramerization domain here in blue, okay, which will be below the voltage sensing domain for that blue subunit. Okay, here in green we have the T1 tetramerization domain for the green subunit of the voltage-gated potassium channel. Okay, and finally, here in orange is the orange subunit's T1 tetramerization domain. Okay, right, now, below this then, here are the N-terminals dangling down from these T1 tetramerization domains, and they might have inactivation balls, they might not. Okay, let's imagine that it's a tetramer that doesn't have inactivation balls, so all of the 4 alpha subunits are non-inactivating alpha subunits. And now what you end up with is another tetrameric arrangement dangling below, basically. Okay, so each one of these alpha subunits ends up with a beta subunit attached onto it here. And here the 4 of them are dangling below, and they're much bigger than the T1 tetramerization domain. So when you see these things, they are much, much bigger than the tetramer of the T1 tetramerization domains. Okay, so let me try and colour this in then here. So here is the beta subunit that is attached onto the blue subunit here. Okay, so this is now a beta subunit that we've attached on. It's a separate protein that has been attached on to the blue alpha subunit. Okay, and here is the red subunit's Kv beta subunit here, which I'll also colour in red, like so. Here is the green alpha subunit's Kv beta subunit here. Okay, and then right at the back then, you'll then have the orange alpha subunits, Kv beta subunits. So these 4 separate proteins here are Kv betas, and each one of them will either be a Kv beta 1, or it'll be a Kv beta 2, or it'll be a Kv beta 3. They can all attach on to the N-terminal region of the alpha subunit of a voltage-gated potassium channel, and they then tetramerize below the voltage-gated potassium channel in this way shown here. Okay. Now, this then can give voltage-gated potassium channels which were built out of alpha subunits that did not have inactivation balls, N-type inactivation. Again, the reason is that these Kv beta subunits, they can have inactivation balls. In fact, they do have inactivation balls of their own. So I'll show this for this blue one here. So here it has a chain with an inactivation ball on the end. Okay, and that means that by adding these beta subunits onto these non-inactivating alpha subunits, you have now effectively added an exogenous inactivation ball that can now go through those natural windows and then gain access to the internal pore, unfold, and then insert itself into the internal pore to block the internal pore and give the voltage-gated potassium channel an N gate, okay, an N-type inactivation gate, or this fast-type inactivation gate, which inactivates the voltage-gated potassium channel much quicker than the C-type inactivation gate would do. Okay, so the addition of these beta subunits then onto a voltage-gated potassium channel tetramer can hugely change the rate at which the voltage-gated potassium channel tetramer will inactivate. Okay, right, so that now concludes our discussion of voltage-gated potassium channels. In the next video, what we'll move on to is a group of very closely related potassium channels called the calcium-activated potassium channels.